You guys see the squiggles?
Yes.
Okay, cool. Just making sure. All right, so let's get to it. So we're going to be building on the limits today. And so first we're going to need to know a couple rules that are going to be useful for limits. And there's 7 of them. And they're based off of the assumption that the limit as x approaches a of f of x and the limit as x approaches a of g of x both exist. So if both of these limits exist, then these rules will hold true. Okay? And so here we go. So the limit as x approaches a of f of x plus g of x, where both of them are in brackets, what ends up happening here is the limit can be like it's distributed. So the limit of the individual functions is the same as the limit of the functions added up and then taking the limit. Does that make sense? And then by the same token, if addition works, obviously subtraction will also work. And so I'll have the individual limits. Their difference is also going to hold true. Okay. The third rule tells us that if we take the limit as x approaches a of some constant times f of x, that's the same as the constant times the limit of the function being produced. So what's interesting here is basically it's saying the constant has nothing to do with x, and so it can be done after the fact. Okay, that's going to be something that's going to be useful, and I strongly recommend if you have constants, to pull them out, just because it'll have you dealing with smaller and smaller numbers. The limit as x approaches a of the product of functions is equal to the limit of the individual functions then being multiplied. I'm sure you guys are like, oh, this is tedious, but you'll end up finding out that when we put all these rules together, it becomes rather cumbersome. So don't take them for granted. Please know these limits well, as it will be important. Since product rule works, obviously division will have to come into play. And so the quotient comes in, and what this is going to tell us is the limit of the function divided by the limit of the other function is the same as taking the quotient of the functions and then doing the limit. You'll get the same answer. Something cool is the limit as x approaches a of f of x, and then that raised to a power is the same as taking the limit first and then taking that number that we have, and it shouldn't be a letter, it should be an n. What ends up happening here is the limit of the function to that nth power is going to be the same thing. And then the last one, which it's one and the same with 6, but most people don't see it that way. The limit as x approaches a of the nth root of f of x is equal to the nth root of the limit of the function. Nothing too crazy, right? How many of you guys are like, all I see is letters? Yeah. It's understanding what function notation is, but that's okay. We'll get through it, and I will help you guys. Okay, let's do an example so you guys can see this. Do you guys need a second to finish copying these down? I'll wait. I'll wait a second. Part of the reason why I do put the notes up for you guys the way I do is if you do miss something, you can always double check your notes with what I have posted. Because having good notes is imperative, right? It's really, really going to be important. And so I want you guys to have that there available. I'm not trying to hide my stuff from you guys. I want it to be tools that you guys can use so it's to your benefit. So,
Professor, I have a question.
Yes. Yeah, no problem, Sophia.
I forgot to ask this earlier. For the discussion,
yes.
Do we have to have a question and reply to students by Friday? Or?
No. It's always by Saturday at midnight.
Okay, by Saturday.
Yeah. I always try to give you the full week. So what I'm going to do is I'll have the discussions posted for Sunday at midnight, so in the early morning of Sunday, and then till Saturday at midnight. Yeah, just I want to give you guys as much time as possible, and really the if I'm honest about the discussions are more about you guys coming up with a collaboration for yourselves, right? So you guys get to realize that, oh wait, I need some study partners, and I'd like to do that. So one thing that I can do for you guys too, if you guys, I don't know if you have your own Zooms, I'm sure by now you probably do. But if you don't and you guys want to do like study groups, let me know. I can set up Zooms for you and have you guys meet and let you have presentation controls so you guys can work on stuff together. I totally don't mind doing that. Okay? It's a brave new world, so I'll give you guys some freedom with that. Okay, are you guys ready for me to move on?
Yes.
Okay, so let's do an example. And so this example, what I'm going to do is I'm going to write out every step. It's going to be tedious. Last time we met, I just did a direct substitution into a problem because I knew it wasn't going to be undefined. Remember me talking about direct substitution? Well, it's important. If I give you a problem where I ask you to show steps, you need to be able to show these 7 steps and what you're doing, and so that's what I'm going to do here, okay? So in this problem, the first thing that I'm going to do is, since I have a power on the outside on each one of these, see I have the limit? So since I have the limit of a product, I'm going to use number 4 first, okay? So I'm going to use number 4 first, and I'm going to go, okay. It tells me that the limit as x approaches -1 of x squared plus 1 cubed times the limit as x approaches -1 of x plus 3 to the 5th power. That was using rule number 4, right? Now, by rule number 6, I know that I can rewrite this thing to be the limit as x approaches -1 of x squared plus 1. Now this whole thing cubed times the limit as x approaches -1 of x plus 3. This whole thing to the 5th power. And I really should have parentheses here because the limit is not only hitting the first term, it's hitting that whole quantity. Okay, so that's important. I really could even break it further than that. Since I have a limit with an addition, I can go back and use the first rule and go, here I'll draw an arrow, go the limit as x approaches -1 of x squared plus the limit as x approaches -1 of 1, that whole quantity cubed times the limit as x approaches -1 of x plus the limit as x approaches -1 of 3, that whole thing to the 5th, right? And I really could keep going on where that x to the 5th, or x squared here, I could have broken that up, but I'm not gonna. At this point, this is shown enough of the understanding of the rules. I'm going to direct substitute. Okay? So, oh, sure.
So how did you determine before you drew the arrow, like where the arrow is coming from, that it was going to be addition and you're going to use the first one?
Okay. How did I determine that?
Yeah, how was that determined that it was addition?
Okay, so very cool. So I'm looking at this guy only, right?
Okay.
So if I'm looking at this, it's the limit of 2 terms being added, right?
Yes.
And if I go up here, isn't this 2 terms being added?
Yeah.
So that's why.
Oh, okay. I was like, I didn't know what it.
No. 100% I understand. And this is exactly what I want you all to do for me, is to ask questions so I can clarify so that you best understand. Okay? So don't ever feel bad about that. I actually really appreciate it. Okay? Okay, now from here what I'm going to do is I'm going to apply the limit to each one. Yeah, Carol, I did. This is now going to become a -1 squared, right? Here, that's just a number 1. Does the limit do anything to a constant? What do you guys think?
I don't think so.
It does nothing to it. So the limit has nothing, there's no x there, so you're just going to end up with that constant. Okay, so that means I'm going to go +1, and then I have to remember that it's cubed. Then times, I'm going to have my other bracket, and so I'm going to get a -1 plus 3, and that's to the 5th power. So I'm going to get 2 to the 3rd times 2 to the 5th, which will give me 2 to the 8th. And 2 to the 8th is, we all have it memorized, right? It's 256. I'm just kidding. I have it written down.
Professor, actually, I have a question.
Yes.
So for that last step that you did, the -1 is from the limit, right? That you plugged it into the x?
Yes, perfect. So when here, it's the x is approaching -1, and so what I'm doing is I'm substituting it in for this value, for this x variable, and for this x variable.
Oh, all right. Thank you.
Yep.
Okay, so yeah, essentially what you do is that you plug in what's the limit, correct?
Correct.
That's essentially what you do.
Correct. Because so to be clear, because I don't, it can be a little bit confusing, because last time we talked, I said when we take the limit, we get super close to the number, but we never get to the actual number. Correct? Do you guys remember me making a big deal about that?
Yeah, because
So
It gets the neighborhood, but not the house.
correct. So in this case, what I'm showing you guys is, wait, you're going to the house, Montiel. You're plugging in that number. And what's really happening here is we're saying this is an approximation of what's happening. So the limit as it's approaching 1 is, where is it tending towards? It's tending towards 256. And the way we do that when we're tending towards it is we do a direct substitution with what the limit is. Because really what I really should be plugging in is a number like 1.99999999999. But what is that essentially? That's essentially 2. Does that make sense?
So we're just basically using whole numbers as opposed to just
So, yeah, some infinitesimally long decimal that, I mean, our calculators, if you go 1.99999 on your calculator plus 1.9999 on your calculator, it's going to spit out 4, right? And so what we're doing here is we're essentially just saying, all right, look, where's it going towards? It's tending towards this 2. We can directly substitute. If we end up with something undefined, like I showed you yesterday, we use a number that's very close so we can see if it's positive or negative infinity. Does that make sense? I'll take the silence as a maybe.
Yes, yeah, that makes sense.
Okay,
Yes.
all right. Absolute value. So many people don't know what absolute value is. It's crazy. I'm about to blow your minds with absolute value. Okay? So, I should have writing. Absolute value of x is equal to what?
X or positive x.
Okay?
I'm not sorry.
So it's equal to x if x is positive. That's true. What else?
It's equal to x if x is negative.
It's equal to negative x.
It's equal to negative x, or it's x negative.
That's right. If x is less than 0. But what else? Yeah, Sharon, you put that. It's 0, and that's when the specific case of when x is equal to 0. A lot of your teachers end up putting the x with the first one, the 0 with the first one, and they say x is greater than or equal to 0. But they're really 3 different cases. Okay? What's imperative and important about this is we're going to do problems where you need to know what the absolute value is. Okay? And so I'm going to show you an example of something where it's important that you guys understand the absolute value. So in your math classes, what would you get when you got the square root of x squared?
X,
That's wrong.
x plus or minus.
And that's wrong. It's the absolute value of x. Want me to show you why?
Yes.
Okay, so check this out. So if I gave you negative 2 squared, square rooted, you told me it was x. What's my x in my problem?
Negative 2.
Oh, cool. So tell me when square root is equal to a negative 2.
Never.
Ever. It's never true. The rule that your teachers would show you in your algebra classes, which they should not have done this, is they would do this and call it x, and then they wouldn't write this down. If x is greater than or equal to 0. Then that's true. But when they don't write that, they have to put the absolute value. And the reason that happens is because of this terrible mistake that happens. Okay? But when we're dealing with limits, we need to know how to substitute for a case like this. And so I'm going to show you how to deal with a case like that. Okay? So let's do it. Here's an example. So in this example, we have x is approaching a negative 6, right? And what we can do is we've got to look at this absolute value piece, right? So now going back to limits just to make sure that you guys completely understand this. What does this mean here? Which way am I approaching negative 6?
You're approaching from negative infinity.
On both sides?
from both sides. That's important. We're coming to it from both sides. Because remember, I told you if it's one-sided, I either have that plus above the number or a minus, which would make it a one-sided thing. In this problem, yeah, in this problem, I'm coming from both sides. And since I'm coming from both sides, I need to be concerned about the absolute value. So, check this out. I'm going to treat this problem with that concern. And so I'm going to look at two one-sided limits. Okay? So I'm going to go the limit as x approaches negative 6, and I'm going to come from the negative side. Okay? I'm going to have 2x plus 12, and then in the bottom, since I'm coming from the left, if I had come from the left, what number would be in the absolute value? So it wouldn't be negative 6. It'd be something a little bit smaller than negative 6.
Would it be negative 6.0001?
That's it. Since we're coming from the left, we need to remember our number line. If this is negative 6 and I'm coming from this direction, that number that's really close there is negative 6.0001, whatever, right? So what number falls inside the absolute value? Is it positive or negative? It's a negative number, right? Because negative 6.0001 plus 6 gives me a negative 0.0001. Do you guys agree?
Yes.
Okay. Since we have that situation, we need to use the negative case. And so we substitute this as negative x plus 6. And I'll go back to that example that was negative 2 in a second, so you guys see why that becomes positive 2. So now here, I'm going to get the limit as x approaches negative 6 from the left. I'm going to factor out a 2. And we can see that we get negative 2 as an answer. Right? Okay. Now remember, in order for the limit to exist in this original problem, coming from the left and coming from the right have to be? They have to be equal, right? So let's see if it's going to be the same thing as I come from the right. Now, if I come from the right, I'm going to have a negative 5.999999. What's in the absolute value? Isn't it a positive number?
Yes.
And since it's a positive number, I need to use the positive case, which is just x. X is what's inside the absolute value. That's x plus 6. So then what ends up happening, some simple algebra occurs, and I'm going to get 2x plus 6 over x plus 6, which gives me 2. Are they equal? So that tells me that this is D and E. We okay?
So we did like two different problems because it was like absolute value. Because there was like the negative.
Correct. You should always look at the absolute value. What is going to make the what's in the absolute value 0 is our critical number that we need to look at. So in this case, the critical number is negative 6. Right? Now, I want to go back to that original problem where I told you, when is this true, right? This is never true. But if we look at it and define it this way, what ends up happening is I'm going to get that square root of negative 2 squared is going to be negative 2. because I end up using this case. And what does that become? Positive 2. Right? The way that your teachers probably taught you this in the past is they said with certain problems you can't just cancel the root with the power. You had to become 4 and then go to 2. Right? They made you make the whatever was under the root become a positive number, and then you could take the root of it, right? Well, that's not true. By the definition of absolute value, because this is actually absolute value, this is the case, and that's your answer. I told you you'd be learning some algebra. You're going to be learning some algebra. Okay, should we do another example?
Yes.
All right, so let's look at this one here. So in this case, we're again going to look at it coming from 2 directions, right? Because we see that 3 does something. Above 3 and below 3, what's in the absolute value is going to have different signs, right? And so we have some concerns there, and so we need to address that. So I'm going to treat it as 2 one-side limits. So I'm going to get the limit as x approaches 3, and I'll go from the left. And I'm going to go 2x, and then what's going to happen if I come from the left? Is it going to be positive or negative?
Negative.
It's going to be negative, so I got to use the negative case, and then I'm going to go x, x minus 3, right? And now I can distribute, and I'm going to get the limit as x approaches 3 from the left of 2x minus x plus 3, which is going to give me the limit as x approaches 3 from the left of x plus 3. Now with substitution, I'm going to get 3 plus 3, which gives me 6. Do you guys agree? Okay. Now I'm going to attack it from the right. So I'm going to go the limit as x approaches 3 from the right of 2x. And now it's going to be a positive number, right? So I'm going to keep the plus. And I'm going to get x minus 3. And then combine like terms. Oops, that should be an x. My apologies. And that will give me 9 minus 3, which is 6. Do they agree?
Yes.
So the limit of this thing is 6. And really I should have done this. And it's probably my apologies. Because if I don't write it that way, what's the limit affecting only? Here, I'll point it out so you guys can see it. If I don't have the brackets, what's the limit only dealing with? It's only dealing with the 2x. So I need to have the brackets or parentheses or something for that. Okay? Just notation stuff. Be careful with it. Are we okay? Not so bad? All right. Okay.
Professor, so when we do the absolute value, we're going to use like the 7 rules that you explained earlier?
So when we do the absolute value, we're going to be using these. So you're going to have to make some judgment calls on this. Does that make sense?
Thank you.
Yeah. Okay. Have you ever seen this notation? The greatest least integer? No? Okay. Yeah, it's funny. I try to show it when I teach Algebra 2, or intermediate algebra, I guess is what we call it. I always try to show the least greatest integer, because it's important for you guys to get it. So I'll just explain it to you guys in a way that kind of makes sense. Any number that isn't an integer drops down to the closest integer. So if I had 2.4, 2.4 would actually be equal to 2. 2.9 would also go down to 2. Now 3.1 would go to 3. Does that make sense what I'm saying?
It just becomes a whole number? Or?
Yeah, it becomes an integer. And so the integer that it goes to is the least integer, the one below it. So I'll just show you a quick picture, because a lot of people end up getting kind of confused with this, and so I want to be able to help you. So if you're 0, you're going to get 0, right? But anything up to 1 is going to be, and here I should do this in a different color so you guys can see this. From 0 to 1, it's going to be 0. So if I get 0.7, it's going to be 0. If I get 0.9, it's going to be 0. If I get 0.99999, it's going to be 0. When I get to 1, it's no longer going to be 0. When I get to 1 going to 2, what's going to happen is I'm going to jump up, and then it's going to be any number between 1 and 2 is going to become 1. Does that make sense?
Yes.
So if I gave you guys 25.1, what's that going to be?
25.
Yes. 24.7.
24.
Good. Negative 3.1.
Negative 3.
Negative 4.
1.
Lowest one.
You drop down. So it gets trippy because when you get to the negatives, you think, oh, 3 goes to, negative 3.1 goes to 3. No, that makes you go up. You need to go down. Does that make sense? So careful with that.
Yeah.
Any negative, actually, instead of being that first digit, it goes down a digit.
Okay.
Does that make sense?
Yeah.
All right. So negative 3.1 is negative 4. 3.1 is 3. Cool?
Yeah.
Okay, cool. Now, something to say with that, now that we're looking at the graph, since this function is discontinuous, right? What's going to end up happening is the limit won't exist at an integer. Okay? So the limit as x approaches a of the least greatest integer won't exist at any integer number. Do you want me to show you why?
Yes.
Yeah.
Okay, check this out. And I can do it with this picture. If I'm going to 1, right? So if I say, all right, the limit as x approaches 1 of this least greatest integer, as I'm coming to 1 from the left, what is the limit? Look, as I'm coming to it from the left, what is the limit?
0.
It's 0. Right? Because the limit really is what the y value is. So what's the y value as I'm approaching 1 from the left? It's 0, right? But what happens as I'm coming from the right? It's 1, right? Since the left is 0 and the right is 1, at that integer, they're not the same value. It's DNE. Agreed? We agreed? Okay.
Explain that one more time?
Yeah.
Sure. No problem. So as I'm coming from the left, the y value for this thing till I get to 1 is 0. Agreed?
Okay.
Yes.
As I come from the right, it's 1.
Oh, yeah.
Since this one's 0 and this one's 1, they're not the same. The limit can exist.
Oh, okay, okay.
Oh, I see.
So the limit would exist if it was just like a flat line.
So check this out. I'm about to show you one that will exist because I want you guys to be able to understand it. So the limit as x approaches 1.5 of this thing, let's look. 1.5 is right about here, right?
Yeah.
Okay? So what is it as I come from the left?
What?
It's 1. Now what about when I come from the right?
What?
They're both 1. They agree. So that means the limit is 1.
Oh.
Okay.
Oh, so good question, Isaac. So here's the deal. If I tell you, if I just give you, and I did this last time, but I want to reinforce it. If I say the limit as x approaches a, that's a two-sided limit. That means I have to come from it from both the left and the right-hand side, right? If I say the limit as x approaches a from the left, that means I'm only coming from one side because I have that little negative there. If I say the limit as x approaches a from the right, that plus tells me I have to come from the right. Make sense? Okay, cool. Now, I want to show you something though. I can make the limit exist from one side. And we did it already, but I want to reinforce it. So if I say the limit as x approaches 1 from the left of this function, we know that that was what?
0.
That was 0. The limit as x approaches 1 from the right of this function, we know was 1. So you can have one-sided limits that exist, but the two-sided limits don't exist because they don't agree. They don't equal. Does that clarify that for you guys?
Yeah.
Okay. Can you guys tell I love this stuff? I really do love it. Okay, cool. So you guys don't need me anymore. What's the answer to this example?
3 does not exist.
Does that make sense?
Yeah, because it can't. It doesn't match up in the middle. Because it comes from both sides, correct?
Yeah. Since it's coming from both sides, it's going to be coming from like 2.9, but 2.9 plugged into that would be what? A value of 2. If I come from 3.1, what's that going to be? It's going to be a value of 3. So one's 2, one's 3, they don't agree. This will not work.
Can you like draw that out?
Sure.
Because yeah, it was.
No.
I want to see how to get to
No.
that fast.
Don't worry about it. No problem. So I'll use blue. So boom, open. Boom, open. Boom, open. And then I'm going to need one more. Right? And so this one's going to go boom, open. So we're trying to get to the value 3. Oh, I should actually 1, 2, 3, 4. Yes, perfect. So there's 1, 2, 3. So look at it. If I'm approaching 3, right? 3 is going to go right here. So if I come from the left, what value is that?
2.
2. And now when I come from the right, what's the value?
3.
It's 3. They don't agree. Boom. D&E. Now, if I gave you something crazy like the limit as x approaches 2.3784566 6, 2, 1, who cares, 9, 8, 7, 6, 1 of this thing, what's that?
2.
It's 2. So this whole thing ends up equaling 2. Right? Since it's not an integer, we know it's going to drop down. From both sides, it's going to work. Got it?
Yeah.
Do you only do the big decimal number like once? Like it would just be placed like at 2.378 and then you would just like go down?
Yeah. Wherever 2.378 blah 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 is, like depending on how precise you want to be, it's somewhere around here, right? But when I look at that, no matter which way I go at it, I'm going to fall right here. Does that make sense?
Yeah.
Okay. Cool. How you guys feeling?
Alright. Feeling better than I did an hour ago.
All right, cool. All right, so let's do some stuff. So this problem right here, or this says that if the function f of x is smaller than or equal to some function g of x, when x is near a, that means the number it's approaching, except possibly at a itself, then the limit of f and g both exist as x approaches a, then this must be true. I'm sure this doesn't make a lot of sense to you guys, but I'll draw it for you. If the function f of x is smaller than or equal to some other function g of x, then as they approach some number a on the x value, it makes sense that the values or the limits of the f of x function would have to be smaller or equal to all the values of the g of x function. So the limit, I'm changing color on you guys, I don't want to do that. I want to be a little bit consistent here. So the limit as x approaches a of f of x will then have to hold to be smaller than or equal to the limit as x approaches a of g of x. Do you guys want a picture? Okay, picture. So let's say that this is my f of x function. Okay? Let's say that this is my g of x function. Right? So everywhere on the function, g of x is bigger than or equal to f of x. Agreed? Okay, doesn't matter where I put a, the limit of f of x is going to be smaller than or equal to the limit of g of x. Now remember, the limit here means a y value, right? It's where it's approaching some y number. So if I had made this my a, is this y value smaller than this y value?
Yes.
Clearly, right? Here, if this is my a, is this y value smaller than this y value?
Yes.
Clearly. So that means that the limits are going to be smaller for f of x than g of x. Now, where they are the same, that's the special case. You see, that's why I have the equal. But that's all that's saying. Okay? Now, the next function, it's called the Squeeze Theorem, actually, this next theorem. All this is saying is if we have three functions, and I want to correct this real quick. This really should be an H here. What this is saying is if we have three functions, a f of x function, which is the smallest, a g of x function that's in between, and an h of x function that is bigger, the Squeeze Theorem tells me this. If I have an f of x function and I have a h of x function and they touch at some point, and g of x is between them, where they touch, g of x has to be the same value too. I'll draw a picture, don't worry. So then what this is saying is then the limit as x approaches a, and this should be equal to L. My bad. G of x will equal L. You guys want a picture, right? Okay, so picture. So here is my f of x function. Here is my h of f function. Here is my g of x function. Okay? Now, what it's saying is, at a, at some number a, where f of x and h of x are the same limit, meaning their y value ends up being the same, this g of x squiggly line, since it's between the two functions everywhere, where they're touching, it has to touch. It has to have the same value. That's what the squeeze theorem is saying. Think of it like a sandwich, right? We have a sandwich. When we put the other sandwich on it, what's everything in between the two pieces of bread? They've come together to become one sandwich. That's what's happening here. Sometimes the squeeze theorem is called the sandwich theorem. Make sense? Okay. Now, the next thing I want to talk about is direct substitution. We've done it already, but I wanted to point out when you can do it, and here's when you can do it. If you have a polynomial or a rational function, and the thing that you're plugging in is in the domain, meaning it makes it real, then we can do direct substitution. And what that looks like is this. If I take the limit as x approaches a of f of x, that will equal f of a. And f of a really is your y value, right? A is the x number plugged into the function. Right? What happens here for a lot of people is a lot of the calculus that gets confusing. It isn't the calculus that's so much confusing, it's their understanding of algebra and function notation. Right? So if a quick example on this, if I had said, okay, f of x is equal to x plus 2, right? And then I said, okay, I'm going to take the limit as x approaches 3 of this function x plus 2. Doesn't x approaching 3 mean, hey, plug in f of 3? And f of 3 would be 3 plus 2, which is 5. So this has to be equal to 5. That's all direct substitution means. It's a line. I know a line is defined everywhere, so that means I can directly substitute in. We're good? Okay. Let's do another example. So in this example, x is approaching 2, and what we need to do is we need to check if the denominator is going to be 0 if I plug in 2. If it's 0 when I plug in 2, then I need to look at it as one-sided limits. So let's look at the denominator. 2 squared is 4, plus 6 times 2 is 12, so that would be 16. 16 minus 4 is 12, right? So since it's not 0, I can directly substitute in this problem. So I'm just going to go 2 times 2 squared plus 1 over 2 squared plus 6 times 2 minus 4, which is going to give me, what is that, 4, 8, 9 over 12, or 3 over 4, and that's my answer.
So to determine whether you directly substituted, what would you do? I'm sorry.
So I check the denominator because since this is a rational function, I need to check to see that the domain is holding true at the number 2 because that's my A, right? This number 2 is my A, right? So now the only thing that's going to make this thing not work is if the denominator is 0.
Okay. So you plugged in 2 to the denominator?
To make sure that it wasn't 0.
Oh, all right.
Because if it would have been 0, then I would have approached it from the left and from the right and then seen, okay, are they going the same direction? Does that make sense?
Yeah.
Okay, cool. That's direct substitution. All right. We have one more example to do, and then we'll go on to
I have
the
a
next
question.
section. Yes, sir.
If the limit did make the denominator 0, then would it be, say for example, if that 2 would have made the denominator 0.
So we did one like that last time. Do you remember where I had one going to negative infinity and one going to positive infinity?
Oh, yeah.
So that was an example where the denominator was 0, and then you'd have to look at it from each side and see, are they both going to positive infinity? Then the answer would be positive infinity. If they're going different infinities, then the answer would be D and E. Do you recall that?
Yes, I do.
Okay, cool. Good question. Okay, so you guys started feeling comfortable, right? All right, time to make you feel uncomfortable. Here we go. So this problem requires some techniques. Okay? Whenever you have a radical, you're going to want to multiply by the conjugate. Okay? So when we multiply by the conjugate, what we're going to end up doing is doing this. And it's interesting. Look what happens when we plug in negative 4 here. Doesn't that make the denominator become 0? So it becomes something that is potentially problematic. But I want to see if I can eliminate x plus 4 from the denominator. If I can eliminate x plus 4 from the denominator, then I don't have to worry about the denominator being 0 in the original problem. Isn't that weird? Because we know it's going to be undefined at negative 4. But if I can cancel out x plus 4 from the denominator, I don't care anymore. And here it goes back to, it's the neighborhood, not the house. Okay? So, looking at this, what I'm going to do is I'm going to go, all right, the limit as x approaches negative 4 of x squared plus 9 minus 5 over x plus 4. And then I'm going to multiply, like I said, by the conjugate of the radical term. So that's a 5 there. To both the numerator and denominator. So what's going to end up happening is we can see that what's the radical. We see that it's a difference of squares, right? On top, it's the factors of a difference of squares. So what ends up happening is the first term squared is square root of x squared plus 9 squared gets rid of the square root. So I'm going to get x squared plus 9 minus the 5 squared, which is going to give me 25. Okay? The denominator, I'm not going to mess with. Because remember, I'm trying to get rid of that x plus 4. Now, I can manipulate this a little bit. And I'm going to go x squared, I think that's minus 16. Are we okay? And that's factorable. So I'm going to get x minus, or I'm going to go x plus 4 and x minus 4 all over x plus 4 root of x squared plus 9 plus 5. Look what happens. Doesn't the x plus 4 go away?
Yes.
Awesome. So we get x minus 4 over the root of x squared plus 9 plus 5. And now I need to check to see if the denominator is going to be 0. If I plug in a negative 4 squared, isn't that 16? And 16 plus 9 is 25. The root of 25 is 5. And then 5 plus 5 is 10. Oh, not 0. So I can now directly substitute negative 4. So plugging in the limit, I'm going to get negative 4 minus 4 over the root of negative 4 squared plus 9 plus 5. That's going to give me a negative 8. We said that that was 10. And so our answer is a negative 4/5. So the limit of this problem is a negative 4/5. What's cool, just so you guys know, if I were to look at it kind of pictorially, it would look like something like this. This would be the value negative 4/5 if that was like the x-axis. And let's say this was negative 4. That's what's happening. It ends up being a hole there. But coming from the left and coming from the right, they're both equal to a negative 4/5. Does that make sense? Cool. That's not an accurate picture, but you get the idea behind it. All right. That's 2-3. Feel good? Not too bad? All right. Do you want me to do 2-5 and then we'll call it a day after that? Okay. All right. Let me go on to 2-5. If you need to go to the restroom or something, by all means, go. That's why I record stuff so you guys can watch it whenever you want. I just want to give you guys time to be able to get to the homework. Now, remember, in one of the homeworks, it's going to have problems from 2.4. Do not do them. I will edit them out. All you have to do is 2.3 and 2.5 homeworks. Okay? All right. Let me go on to 2.5. Not now. See, this is the stuff I would have shown you, but I'm not gonna. You would have been tripping, and I don't want to do that to you this year. All right. Continuity. So continuity is a very big topic. Most of us, we've learned something is continuous in mathematics if we don't have to lift our pencil, right? That's been the, oh, what's continuous? Oh, look, that's continuous. Why? I didn't lift my pencil. Well, we don't do that in calc. We have reasons for everything. It's messed up. We need justification for everything that we're doing. Okay, so what's cool is I'm just going to be reinforcing some things for you guys too, which is cool. So in order for a function to be continuous, okay, at some number a, the limit as x approaches a of f of x is going to equal f of a. We have three things that must hold true. Okay? The first is that the function must be defined at that x value a. Okay? Meaning that f of a has to be some real number on the function. Okay? 2, the limit as I approach A must exist. Okay? And 3, the limit as x approaches A of the function must equal that defined point at A. Okay? It's a big deal. Now, I can show you a picture. Probably a picture is worth 1,000 words. So check this out. Continuity. So if I give you, I'll use a different color. If I give you a function, boom, 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 is that continuous?
Yeah.
No.
It's not. Why?
It has a hole.
It has a hole and it has a removable point, right?
It goes up.
It's got the removable point. But watch this. Does f of a exist? If this is a, does it exist? Yes, it exists. Does the...
Because it's a value, but it's just removed.
Correct, yeah. Because this would be f of a right here, right? This guy is f of a. Does the limit at a exist? Yes, it does. As I approach from the right, from the left, am I approaching some, I'll write it now, some limit value L coming from the left? What's it approaching? Isn't it going to L? As it approaches A, what's the limit going to? Isn't it going to L? Right? As I come from the right, what's it going towards? It's going to L, right? So the limit as I approach A is L. So both the first point and the second point work. So right now it looks like it's continuous. But it's the third point in this case that fails. Is the limit equal to f of a?
No.
The answer is no. And since the answer is no, it fails. If it fails any of the 3 points, it's not going to be continuous. Make sense? Now, had I removed that and put the point here, the limit would have been equal to the f of a value. This thing would have been continuous. You guys with me?
Yes.
Okay, very cool. All right, so let's show there's also the possibility to be continuous only from one side. So you can be continuous from the right, you can be continuous from the left. Okay? And so let me show you guys that real quick. So the 3 conditions that must hold is the limit, or f of a is defined, meaning that f of a exists, right? 2, the limit as x approaches a from the right of f of x must exist. And for this case, the third point for one-sided is that one-sided limit of f of x must equal f of a. So let me draw a function so you guys can see it. If this is a, and this was my function, does f of a exist? Yes. Does the limit as it approaches a from the right exist?
Yes.
Yes. And are they equal? Are they equal?
Yes.
All 3 conditions end up holding true. So look, f of a is this value right here, whatever that would have been on a xy plane, right? That's f of a. The limit as it approaches a is L, right? But it exists. That's what matters. Is that L equal to f of a? Yes. So it holds all 3. this would be an example of something that is continuous from the right. Okay? This one's the same principle. Everything's the same except for instead of pluses, there are going to be what? Little minuses, right? So now it's this shaded in piece and it looks like this. That's going to be continuous from the left. Because I'm approaching from the left-hand side. That's what that means. Here, I'll write it down just so you guys have it. Do you guys have it copied down?
No.
Okay, no problem. How's the pace?
Good.
All right. All right, can I move on? All right, so here we go. So this is a big idea. It says a function is continuous on an interval if it's continuous at every number in the interval. Okay, that makes sense. That means I need to check every single number in an interval to make sure that something is continuous. Well, I'm going to show you how to do that. F is continuous on the open interval from the left and from the right, and is continuous from the right at A and from the left at B. So the right endpoint, the left endpoint, I'm sorry, and the right endpoint. So the right endpoint, the left endpoint is A. The left endpoint must be continuous from the right, and the right endpoint must be continuous from the left. That should make sense though, right? Or do you want me to draw pictures so you guys can see?
Take a picture.
Okay. So this example that I'm going to do right now looks like this. Boom. Right? Now, this is -3, this is 3. The left endpoint is -3, right? This is the left endpoint, but to be continuous, I need to approach it from I have to come to it from the right. The right endpoint, in order to show continuity, I need to come to it from the left. Because, can I come from the right? How do I know which way to approach it? It makes no sense. I have to come from the left. How do I come to this one from the left? I can't. I have to come to it from the right. Does that make sense? Pictures help. Okay. So, I'm going to show you the steps in order to be able to do this. The first one, notice that it said that it's got to be continuous from A to B on an open interval, meaning I need to check every point possible, right? And to check every point possible, I end up being abstract, and I'm just going to use a variable to represent all the numbers between -3 and 3. I'm going to call that guy A, okay? So I'm going to go, okay, let's see if this is true. So condition number one, because we have three conditions we need to show. Condition number one. Does f of a exist? And remember, I'm restricting this to a is between -3 and 3. Okay? Because I'm doing step one. So f of a would simply be a substitution where I get the root of 9 minus a squared. Right? That's what f of a would equal between -3 and 3, whatever number I choose. Agreed? Okay. Number two. The limit as x approaches a, because I don't know what it is, of the root of 9 minus a squared. Since I'm between -3 and 3, I know it's well defined, right? So I can do direct substitution because I'm in the domain. Do you guys agree? Ooh, this should be x squared right here. I'm sorry. Right? I can do direct substitution because it's well defined. And since it's well defined, I know that this is going to equal 9 minus a squared. Well, the third step was to show that they're equal. Are they equal? It is equal, right? So I know that the limit as x approaches a of 9 minus x squared is equal to the root of 9 minus x squared, or 9 minus a squared, which is equal to f of a. So that's telling me they're both equal to that. So this thing is continuous between -3 and 3. Agreed? Now what I need to do is I need to show that it is continuous at -3 and show that it's continuous at 3. So here's how I'm going to do that. So I'll do one of them and I'll leave the other one for you guys to do, okay? Unless you feel uncomfortable, let me know. So step number one, I'm going to go, all right, what's f of -3? I'm doing the left endpoint. I'm going to get 9 minus a -3 squared under the root is going to be 9 minus 9, which is 0. Right? Then I'm going to take the limit as x approaches -3, but I'm coming from the right. Well, I know that that's acceptable within the domain, so I'm going to plug in -3 squared, and I'm going to get 9 minus 9, which is in fact 0. And so that was step number 2. Step number 3, the limit as x approaches -3 of this function is equal to 0, which is equal to f of -3. Since it shows this thing is left, I almost messed up. This thing is right continuous at x is -3. To show the other one, you'd have to plug in, instead of -3, you're going to plug in what number? +3. Once you've shown both of those, plus part 1, you can say that this thing is continuous from -3 to 3. Make sense? I think it's fairly reasonable, but if you're confused at all, please let me know. I don't mind trying to do another example for you. Do you want me to do part 3, or do you guys want to do it?
Can you do it?
Yeah, sure, no problem. Okay, so then for this one, again, I got to show the 3 steps. So I'm looking at 3 because I'm looking at the right endpoint, right? So I'm going to go the root of 9 minus 3 squared, which is going to be 9 minus 9, which will give me 0. The second step is to show the limit piece, right? It's x as it approaches 3 from what side?
Left.
Left.
From the left. So I'm going to put a little minus sign there. So that's going to give me, I won't get all picky. I'm just going to plug it in since I know. I'm going to get 9 minus 3 squared. And that's going to be 9 minus 9, which again is 0. And then the third step, that limit as I come from the left is equal to 0, which is equal to f of 3. And now from here I can say this is left continuous at x equals 3. Cool.
So oh, you go first.
Thank you. On step 3, I don't think I'm seeing it, but then probably am. So you're just like plugging in the 3, right?
Okay, so for step 3, all I'm confirming is that step 2, what the limit was, is equal to the step 1. So in essence, I'm putting the 0 there just to show that they're equal, but I'm saying step 2 is equal to step 1.
So step 3 is just confirming 1 and 2.
Correct. It's saying that, okay, because step 1 is saying f of 3 exists. Okay, it exists. Part 2 says the limit exists. Part 3 says they equal each other. So
Okay, I see it now.
yeah. So
if in the first part you would have gotten like a 4, and then the other one would have been like a 0, they wouldn't be like continuous, right?
correct. They both exist. 1 and 2 work, but they're not equal. They'd fail part 3. Yeah, that's
Thank
it.
you.
Yep. Perfect. Thank you for asking the question. I'm sure there's others in here that are like, oh. Okay. Now we have a theorem, and the theorem says this. It says, if f is continuous at b, and the limit as x approaches a of g of x is equal to b, then the limit as x approaches a of f of g of x is equal to f of b. Well, totally makes sense. Right? Or is it just me? You want me to explain it? All right, here we go. So what it's saying here is this. I'm going to mess with this guy here. Okay? So what did I tell you about the limit? The limit can go inside of a function, right? So I'm going to go, okay, f of the limit as x approaches a of g of x, right? All I did was take the limit and put it where it applies with the x, right? But what is the limit as x approaches a of g of x? Didn't I tell you? What's that say it's equal to?
B.
It's equal to b. Right? So that tells me that this thing in the parentheses is equal to b. So if that's equal to b, then I'm going to get f of b. Make sense? Hold on one second. My father. Okay. Does that make sense to you guys? It makes sense how they got the f of b then at the end? Basically, the limit can go through a function to the part of the function that has the x value or the x variable. Okay? Do you guys want me to show you an example? Okay. Okay, so let's say that we have this example right here that the limit, or it says f of x is equal to the absolute value of x, and g of x is equal to x minus, or 5 minus x squared. And I say, all right, let's call our a 3. Okay. So I'm going to do what is the limit as x approaches 3 of f of g of x. Okay, so from the rule, I'm telling you that the limit can go inside, right? If the limit can go inside, then don't I get f of the limit as x approaches 3 of g of x? Yes?
Yes.
Okay, so now g of x was that 5 minus x squared, right? I can do a direct substitution, so I'm going to say f of 5 minus 3 squared. Agreed? Are we in agreement?
Yeah.
Okay. So then I'm going to get f of 5 minus 9, which is going to give me f of negative 4. But that into f function is going to be negative 4 under absolute value, which is going to give me an answer of 4. Does that make sense? Okay. If you didn't do it that way, it's perfectly fine. I'm going to show you another way, and I'll do it in a different color just so you guys can see it. So let's say that we did it this way. The limit as x approaches 3 of f of g of x. And instead of plugging in the limit into the beginning, I changed it and put in the function. So I went, okay, the limit as x approaches 3 of f of 5 minus x squared. Isn't the f function absolute value? Right? So I'm going to get the limit as x approaches 3 of absolute value of 5 minus x squared. Now I can directly substitute. So I'm going to get 5 minus 3 squared in absolute value. That's going to give me 5 minus 9 in absolute value, which is 4. So what I'm trying to demonstrate is you don't have to move the limit in. You'll still get the same answer. It's just you can see it gets a little bit more complicated because now what you're doing is compositions. Right? Are we all right? There's some stuff to absorb, isn't there? What I'm gonna try to do on Tuesday of next week, I want to spend a good maybe 30 minutes to an hour answering questions you guys might have from homework and stuff. I believe it's important for you guys to see me solving problems for you so that you guys can better understand them. So come loaded with questions for me, okay? Because as much as I want to go over material with you guys, I think it's important that you guys see problem solving being done, and I can talk about how I think as I'm solving the problems. Okay? So any problems you're stuck on, please ask. Okay, there's a new theorem, and this theorem says that if f and g are continuous at a and c is a constant, then the following functions are also continuous at a. So, if f and g are continuous, then I want to do it in black, sorry. Then the sum of the two functions is continuous. So if f is continuous and g is continuous, if I add the two functions, it's still going to be continuous. Okay? If I subtract them, it's still going to be continuous. If I multiply either f or g by some constant, they're still going to be continuous.
Wait, is that G or C?
For 3, that's a c. So c times f is continuous. So basically what I'm saying there is any constant times the function that's continuous is continuous. So if I would have gone c times g, that would also be continuous. It's basically any number I multiply a continuous function by is still going to be continuous. Okay? All right. The product of two continuous functions is continuous. Okay? And then the last one's a little bit weird. The quotient of two functions is continuous, but there's one condition that must hold true. G of A can't be 0. And why is it specifically at A? Because in my thing, I said at A. So if I would have said it like some F, or F, at some M value, then it would have been F, G of M can't be 0. Does that make sense? It's where I'm evaluating at. Okay, and now to save you guys some time. Polynomials, you're going to love them. If you see a polynomial, we know this about it. I'm not going to make you show me. If it's a polynomial, it's continuous everywhere. Isn't that awesome? It's pretty awesome. Rational functions, they're almost continuous everywhere. It's within their domain. So if you have a rational function, it's within its domain. Okay? And then just so you have a list of them, because this is important, I'll leave it so you guys can still see it. Here are all of the functions within their domains that I'm not going to require you to show me that they're continuous. It's a theorem that it's already been proved by somebody. You can just say by the theorem it's continuous. Polynomials, rational functions, root functions, trig functions, inverse trig, exponentials, and logarithmic functions are all continuous within their domain. And then I have one more thing to show you and we'll call it a day. Is that okay?
Perfect.
Or I can stay on and answer questions for anyone who might have questions about homework already. I'm totally fine with that. I'll just stop recording at that point. Okay? Can you guys believe it? We're already halfway through a chapter.
That's
It's like this.
In just 2 days.
I know. And we're only going to cover 5 chapters, but the chapter 6, I'm only going to cover 4 sections, but each section is going to take a day. So
Maybe we'll be done in 5 weeks.
no. Unfortunately, chapter 3 has 10 sections. Chapter 4 has 7. 5 has 4 has 9 sections. 5 has 6 sections, and then 6 has 4 sections. But you got to throw in tests and things, so there'll be some room, there'll be time. All right, did you guys get to write this stuff down?
for Sure.
Okay. Let me do one more theorem for you guys, and then we'll call it a day. So the intermediate value theorem is one you've probably heard of or seen before. It says suppose that f is continuous on the closed interval from a to b, and that n be any number between f of a and f of b, where f of a cannot equal b, then that there exists a c in the open interval such that f of c is equal to n. Totally makes sense. Right? I'll draw a picture so you guys can get this. So let's see, last time I want to make it something pretty. How do I want to do this so you guys can kind of see it? Oops. Okay, cool. So let's say that here's a value, here's a value. I'm going to go, the domain of this thing then, my a and b values, remember they're in terms of x. So where am I going from? From where to where?
Negative 6 to 7.
From negative 6 to 7. So that is my special place, right? And I'm saying that there is some n value, meaning a y value, that is between the lowest y value and the highest y value of this thing, right? I could have chosen anything. I'm going to choose one where it's, let's see if I can find one that's pretty. I don't want to confuse it with the same number. Let's say that I use, who cares? I'm going to use this guy right here. Okay? So this right here. So what's my n? What do you guys think my n is right there? 6. So my n in this case is 6. What they're referring to as your c is this thing down here. So let's call it 4.9. I mean, I could get specific and find out what it is, but this would be my c. Okay? We'll do stuff with this eventually where you're going to look at functions and find a limit value, and then you're going to go find out what the x value is. I just wanted to point out what they're talking about when they're talking about the intermediate value. Okay, now the way that you guys probably used intermediate value back in the days in your old classes was your teacher said, okay, you're going from negative 6 to 7. And then you check, is negative 6 below 0? Right? So negative 6 was 9, or negative 9, right? And 7 was positive 9. Since this was equal to a negative 9 and this was equal to a positive 9, between them it had to cross the x-axis. And so you knew that there was a root. Do you guys remember your teachers talking about that? So that's the way most people have used the intermediate theorem to be something useful. In calculus, we're saying the intermediate value theorem will work for any y value. Not just to find out if there's a root, but any value on the y, we can find out where it hits on the x. Does that make sense? Okay. All right, I'll stop recording and then I'll answer questions for any of you who need any help. Let me stop. Or do you have any questions on this before I do stop? No? All right.